Hi, everybody. So here I am at Hogwarts. I don't know if I mentioned I was sorted. They had a whole big thing because for the first time in Hogwarts history, they're not sure what to do with me because first the sorting hat wanted to put me in Gryffindor, and then it changed its mind and wanted to put me in Ravenclaw and Griffin. But then it's a whole big mess. So I'm either in Gryffindor or Ravenclaw, and I'll let you know whatever I know as soon as I know it. But I'm enjoying my time here at Hogwarts. And speaking of magic, we're going to do a technique of integration called integration by substitution. See, we learned in 5.1, we learned just how to do an integral because we recognized if I have the integral of 3x squared, so we knew that the answer was x to the third because if I take the derivative of x to the third, so on and so forth. And that's true all the time, but it's not always that recognizable. So we're going to do a famous trick called integration by substitution. Again, what we're doing is by the way, in every case, the integral means I'm saying what function do I have to differentiate in order to get this thing that's inside the integral. So that's always. But sometimes it's very easy and blatant to recognize it, and sometimes it's not so simple to recognize it. So we're going to take advantage of something we learned when we were doing derivatives. We learned this idea of chain rule. And sometimes we're going to be able to use the chain rule backwards, if you will, to help us form an integral. Or more precisely, we may look at an integral and be able to notice, if we're very sharp, that chain rule was done on a function to get this answer that's inside the integral. This new function that's inside the integral. So we know from chain rule is that the derivative, if I have f of g of x, it's a composite function, the derivative is going to be f prime of the g of x function times g prime of x. And that's chain rule, and that's what we did. That's what we did already back in chapter 4. Moving on. Okay, I'm actually going to get rid of my, as beautiful as I am, I'm going to get rid of my, rid of me. Sorry about that. But you're still here, man. I'm still here. So let's look at an example here. We want to find the integral. And let me just show you how it works. I think it's easier. Then we'll look at all the fancy stuff. We have the integral of 3x squared times e to the x cubed minus 1. Now, e to the x cubed minus 1, that's like a composite function. And the interior of it is the x cubed minus 1. So it's e to the, function, which makes it f of x, which is x cubed minus 1. Anyway, now, if I would take the derivative of e to the x cubed, I would get e to the x cubed minus 1. I get the same function, but then I have to multiply it times the inner derivative. The inner derivative is 3x squared. Because when I take the derivative of x cubed, I get 3x squared. When I take the derivative of minus 1, it just disappears. But this 3x squared is the same 3x squared that I have over here, which means that the integral now of 3x squared times e to the x cubed minus 1 is just e to the x cubed minus 1 plus c. And what plus c, because that's a constant of integration, because when I differentiate it, it's just going to disappear. So that's really the whole trick. So in other words, I looked at this function here and I noticed, this is where you have to be sharp. You have to notice that the derivative of this x cubed minus 1, the derivative of that, oh, look at that, I can highlight. The derivative of that, I'm gonna make it pink for now. The derivative of that is 3x squared. So I see I have e to something. So whenever I see a function and the derivative of that function, that's a clue to me that we're going to do integration by substitution. Oh, well, that's weird. I'm going to get rid of it. Okay. It doesn't matter. Next, blah, blah, blah. What if you just have this? X squared times e to the x cubed minus 1. So I don't have the 3x squared, I just have the x squared. Well, let's do some magic here. I'm going to take the x squared, I'm going to multiply it by 3 over 3, because 3 over 3 is just equal to 1. Now I'm going to pull the third out of the integral because you're allowed to pull a constant out of an integral. You can't pull an x out of an integral, but you can pull a constant out of an integral. Now in here, I have 3x. Now I have the same easy guy that I had before. So the answer to what's inside the integral is e to the x cubed minus 1. But this 1/3, it just follows along for the ride. And that's going to be my final answer. That's awesome. Okay. Okay, so let's look at some general formulas here. If I have the integral, if I have a function of x, and that whole entire function is raised to the nth power, and then I'm multiplying that times some other function, which just happens to be the derivative of this inner guy, the answer is going to be f of x to the n plus 1 over n plus 1. And because if I take this plus c, of course, because if I take this answer here and take the derivative of it, the n plus 1 comes out to the front, and that becomes this n plus 1 goes out to the front, and the n plus 1 also turns into an n, and the n plus 1 up here cancels out the n plus 1 down there, and I'm left with this guy right here. So it's very, and of course I multiply a chain rule, I have to do the f times f prime. So basically, if I take the derivative of this guy, I get that guy right there. The integral of e to the f of x times f prime of x, that's going to be e to the f of x plus c. Same reason. This is actually the example we just had a couple of minutes ago, where f of x was x cubed minus 1. That was the example we just had a few minutes ago. And if I have something that looks like this, 1 over f of x times f prime of x, well, that's screaming ln. Because if I take the derivative of the ln of f of x, I get 1 over f of x times the inner derivative, which is f prime of x. So these are just some general indefinite integral formulas, which will work very beautifully. Let's look at an example of this. Suppose I have the integral of 3x plus 4 to the 10th power, and then I multiply it times 3. Now, first of all, if you want, in theory, I could take 3x plus 4 and raise it to the 10th power, which means I have to multiply it times itself 10 times. But that'll be a huge, messy thing, because it's like you're doing the, what do you call it, like foiling it 10 times. It'll be like a gigantic, polynomial. So an easier way, but I could do that, and I could integrate each term individually. But an easier way to do that is to say this is a function raised to the 10th power, and the 3 here is the derivative of the inner part. So the answer is going to be 3x plus 4 to the 11th divided by 11, which is my regular power rule for integration. And the 3 was part of the, because if I would take the derivative of this answer, this is what I would get right here. I get 3x plus 4 to the 10th power times the inner derivative of 3. And that's what the check here is telling us. How about this one? The integral of e to the x squared times 2x dx. Well, the answer is going to be e to the x squared, because if I take the derivative of e to the x squared, I get e to the x squared times the inner derivative, which is the derivative of x squared, which is 2x. And again, that's exactly what it's saying right over here. And finally, if I do the integral of 1 over 1 plus x cubed times 3x squared dx, well, if I have the derivative of 1 plus x cubed is 3x squared, so this is going to wind up being ln of 1 plus x cubed, because if I would take the derivative of ln of 1 plus x cubed, then I would get 1 over 1 plus x cubed times the inner derivative, which is 3x squared. And of course the plus c, I haven't kept mentioning the plus c, because the c's just disappear when I take the derivative. So they're important. I haven't been mentioning it that much, but they are very important, and you can see that it's there. Okay, next, where is the next page? Why is it not popping up? What's going on here? Let's try. Here we go. So this is just going to be the okay, we're going to this whole thing with differentials is really just another way of saying what we've been doing the whole time. If dy dx is equal to f prime of x, so that means dy is equal to f prime times dx. And this is, I wouldn't give, whatever. It's easier than it looks. So y is equal to f of x, which is x squared. So dy dx is 2x. That means dy is equal to 2x dx. Just another way of writing it. And if u is equal to e to the 3x power, then du is 3 times d to the 3x dx. So instead of saying du dx like we used to do, we're bringing the dx to the other side. It's almost like we're multiplying out a fraction and bring it over to the other side. And same thing here, dw is equal to 5 over 4 plus 5t dt. When my original function, my composite function is ln of 4 plus 5t. So I don't want to get all hung up on this. It's just notation. Let's look at a problem here. We have the integral of x squared plus 2x plus 5 raised to the 5th power times 2x plus 2. Now, if you notice, I see this thing raised to the 5th power. And the inner function, which is raised to the 5th power, if I take the derivative of x squared plus 2x plus 5, I get 2x plus 2. So that tells me, hey, chain rule here, baby. So if I let u equal to x squared plus 2x plus 5, then du is equal to 2x plus 2 times dx, which, by the way, is exactly what I have right here, 2x plus 2 times dx. And so this winds up being the integral of u to the 5th power times this whole thing, which is just du. But we're gonna, I don't want a flashcard. What does that mean? All right. Now let's go on. Boy, I'm having trouble. Here we go. It's coming. So again, this whole thing here winds up being u to the 5th power times this whole guy here, which is du. Now the integral of u to the 5th power du. Now, why did I do this? I did it because u to the 5th power du is a very simple, straightforward thing to integrate. I get u to the 6th over 6 plus c. The only thing is, this was my answer already, but I can't. But I notice that the plus c pops up as soon as I get rid of the integral sign. There's before that, I'm just like manipulating things. Once I finally dispense with the integral, that's when I come with the plus c. But I have u to the 6 over 6. However, originally there was no u. I just invented a u to solve this. So I have to back substitute and put the x's back in for the u. So I have 1/6 times x squared plus 2x plus 5 to the 6th power. If I would take the derivative of this whole sucker, which is what was showing here in the check, I would get this guy right there, which is exactly what is supposed to happen. And that's what it means. And let's look at some more cool, fun formulas. The integral of u to the n is u n plus 1 over n plus 1 that we know. The integral of du is e to the u plus c. The integral of 1 over u du is ln u plus c. We actually know these already from previous. This is just saying the integration by substitution, just saying in words what we've been explaining the whole time. And wow, it's going so slow. I don't know why. Usually, I don't know why. I don't know why it's going so slow. Here we go. And now to solve these guys using substitution. Again, the inner derivative is 3, so I have the inner derivative out there. And my answer, so this winds up being the integral of u to the 6th, which is u to the 7th over 7. And then I just back substitute 3x plus 4. And so this sucker over here for e, well, again, the derivative of x squared is of t squared is 2t. This just winds up being e to the u du, because 2t dt is equal to du, and it's e to the u plus c, which is e to the t squared plus c, and power, we're done. So these are very, very, very simple and straightforward. Now, let's look at this guy. Let's look at c. So the integral or the derivative, so here I have square root of x cubed plus 5. That's my composite function, because it's like a function within a function. The derivative of x cubed plus 5 is going to be 3x squared. Now here I have 4x squared, so it's kind of close. I have the x squared right, just have a 4 instead of a 3. So what I'm going to do is I'm going to do one of my tricky tricks. You probably know what I'm going to do by now. I'm going to multiply this by 3 over 3, but you'll see, I don't want to give away too much here. And Let's just wait for this to happen. I don't know why it's taking so long. Here we go. So let's look at C. So I'm going to multiply. Oh, so I'm going to do this a little differently. If du is equal to 3x squared dx, that means 1/3 du is equal to x squared dx. So what I'm going to do is I'm going to replace the x by 1/3 du. I already have the 4 over here. So I want to have 4/3, and that 4/3 gets pulled outside the integral. So I have 4/3 times the integral of u to the 1/2 power, which is 4/3 times e to the 3/2 over 3/2, which once I simplify it and then back substitute, I get this guy right here, 8/9 e times x cubed plus 3 to the 3/2 power plus c. And again, if I want to take the derivative of this answer, I will get this guy right here. That's really the whole point. That's always the point. Okay. Now here's a fun one, example 6. Example 6 doesn't look like substitution is going to work. So we have to be a little tricky. Because the derivative of the inner function, if x plus 2 is the inner function, the derivative of x plus 2 is 1. So where did that x come from? So watch what we have to do here. It's going to be very, very tricky. We're going to let u equal x plus 2, which makes sense, because that's the inner function. But if u equals x plus 2, that means x is equal to u minus 2. So what I'm going to do is that the bottom of the fraction is going to become square root of u. The top is going to be u minus 2. So I get u minus 2 over square root. Now, this was even worse than I started with. So why am I so happy about it? Because I could separate this into 2 fractions, and it's going to make everything easy. Because when I separate this, I get u divided by u to the 1/2, which is just u to the 1/2, and then -2 divided by u to the 1/2, which is -2 times u to the -1/2. Remember, when you raise a negative exponent, it does not mean a negative number; it means a reciprocal, which is what I have right there, u to the 1/2. So now I integrate each guy separately. Back substitute, and this down here is my final answer. And it all works beautifully. And again, I'm waiting for patience. Here we go. Okay, now we're going to do some business. We're going to do a price demand equation. So price demand. So the market research department of a supermarket chain has determined that for one store, the marginal price, and the marginal price is P prime. So it's the derivative of the price P of X. P is where P would be the price for X tubes per week. For certain brand of toothpaste is given by P prime is equal to negative 0.015 e to the negative 0.01x. So you want to find the price demand equation if the weekly demand is 50 tubes when the price of a tube is $4.35. And you want to find the weekly demand when the price of a tube is $3.89. So one step at a time. The first thing we got to do is find the price demand equation, which is P of X. So P of X is just the antiderivative of P prime of X, or it's the integral, or I'm saying here, we say the integral of P prime of X. But every time I'm saying integral, I mean indefinite integral. We haven't even dealt with definite integrals yet. There's something called a definite integral. So I'm saying integral, but all these cases are what we call an indefinite integral. Don't stress what that means right now. We will explain it. But the point is that the integral right now we're just looking here is the antiderivative. One way you're gonna know, by the way, you see there's nothing on this big giant S. If there would be a number down here and a little number up there, then that would be a definite integral. It's kind of a different thing. And if I don't have numbers, then it's called the indefinite integral. and it just means the antiderivative. Anyway, we want to get the antiderivative here. So I have a composite function here, and what I'm going to do is I'm going to substitute, I'm going to let u equal negative 0.01x, which is dx is equal to negative 100 du. So I'm going to write, this is the integral of negative 100 e to the u du. I'm going to bring the negative 100 out here, and when I multiply them, the negatives cancel out, and this becomes 1.5 times the integral of e to the u du. And the integral of e to the u is just e to the u, so it's 1.5 e to the u plus c. Now I back substitute because u is equal to negative 0.01, and of course I have the plus c. And that is how we do it. So basically, you have this whole fancy schmancy thing here, but it all boils down to now to the next part. We're gonna substitute 50 for x and 435 for p of x, p, and we're going to use that to actually solve for c. And that's and once we've solved for c, we're going to use that to get this last question of what's the demand when the price is $3.89. But let's one thing at a time. So what I'm going to do now is we're going to find c by plugging 50 in for x, and we know that p of x is equal to 4.35, and we do crunch, and we get that c is equal to 344. And we're using a calculator for all this garbage. And now that means p of x is equal to 1.5 e to the negative 0.01x plus 3.4. And once I have this new equation, I've solved for c. So I needed that second to last question to get the very last question, because the second to last question helped me solve for c. Now that I know what c is, I know the entire equation, entire formula, whatever you want to call it. And now I just want to find what does x equal when p of x equals 389. So I'm going to take this guy right here, set it equal to 389, subtract 344 from both sides, divide both sides by 1.5, and I get this here. Now I take the ln of each side. So I take the ln of each side, the e and the ln of course cancel. I get negative 0.01x is equal to ln of 0.3. So x is equal to, now I just divide both sides by negative 0.01. So x is equal to negative 100 times the ln of 0.3, which is approximately 122. Wait, so where the negative goes, here's a negative, and here I have a positive. How do I, yeah, we have negative 100 ln of 0.3. So where'd the negative go? How come they just kind of ignored the negative? The answer is ln of 0.3 is a negative number. In fact, let's see what that is right now. If I do we're ln, oops, that's not going to do it. 0.3. So is that, now I take the ln of that, I get a negative number. When I multiply this negative number times negative 100, those allowed. No, oh, you have to multiply it by 100 and then do the plus minus. So I get positive 120, which is what they got right here, positive 120. Alrighty. And that's it. That is the end of 5.2. It's been loads of fun, and we'll see you guys next time. Okay, bye everybody. It's been a lot of fun, and we will see you next time. Bye. Let me just show you my beautiful, here I am. I am a human being. I'm here having fun in Hogwarts. Okay, I hear Luna calling. I kind of like Luna, so like, you know, she's calling me now. I want to go to her. Bye.